In this video I want to talk about the difference between the inverting and the non-inverting configurations of an operational amplifier. As you can see here, I have the two diagrams, schematic diagrams drawn. This one is the inverting configuration and this one is called the non-inverting configuration. Now the difference is, if you look at the minus and plus inputs, on the inverting configuration the plus input is grounded and the minus input is connected to the V0 output via resistor R2 feedback, and it's also connected through resistor R1 to a input voltage Vi. So the voltage leaves here, passes through R1, goes into the minus input, then the current goes up, passes through R2 and goes to V0. Now there is no current entering the minus input because we assume, and for the ideal operation amplifier, the input impedance is infinite, and this simplifies the analysis. If you look at the non-inverting configuration, the input is applied directly to the plus input and the minus input is connected again through a resistor R2 to V0 and then through resistor R1 to ground. So the only difference is we swapped for the inverting configuration, the input voltage is connected to the minus input via the resistor R1, and for the non-inverting input it's connected to the plus input here. So we just swapped. This ground is this ground and this input voltage is this input voltage, so it's just swapped. Now as far as the analysis go, let's try to analyze the inverting configuration first and then the non-inverting configuration and see what the differences are. So for the inverting configuration, let's write down what we know. So V0, the output voltage, is equal to the voltage at this node V minus the drop across the resistor R2. So what's the voltage at V minus? Now for operation amplifiers we use the simplifying assumption of the virtual ground, because we just assume that the voltage at V minus is exactly equal to the voltage at V plus. This simplifies the analysis and it's actually approximately true. In the limiting case it will be true, and we just assume it is true to simplify the analysis. And why would we do that? Because V0 is equal to A, which is the gain, times V plus minus V minus. So because V0 is a finite number and A, the gain, is really large, the gain is in the millions, and this means that V plus minus V minus must be a really small number, and this implies that V plus is approximately equal to V minus. So here, going back here, we have that V0 is equal to V minus here, which is equal to 0 volts because it's the same. So this is at 0 volts and this is at 0 volts. So this is equal to 0 minus I times R2, because this is the drop across the resistor R2. So this is V0. Now that we have V0 and we have resistor R2, we need to find out the current. What is the current flowing into here? There's no current flowing to the minus input, so all the current is going through R1 and then R2. So the current I here, I is going to be equal to the voltage Vi minus the voltage at V minus, which is 0, divided by resistor R1. This is just Ohm's law. So this is equal to Vi over R1. So this is what I is. So finally we know that V0 is equal to minus R2 times I. So this is Vi over R1. So V0 is equal to minus Vi R2 divided by R1. So just some terminology here. This is called the closed loop gain. We define the closed loop gain G. Let me actually change colors here. The closed loop gain G is defined to be V0 divided by Vi, and this is equal to minus R2 divided by R1. So as you can see, the gain of the open loop gain of the operation amplifier A is almost infinite if you have no feedback. As soon as you apply feedback, in this configuration, the gain only depends on the resistor R2 and R1, and this can be easily controlled by changing different resistor values. So here we have an amplifier that we can easily control by just changing the resistors R1 and R2. Okay, so now let's have a look at the non-inverting configuration. So this is the non-inverting configuration here, and we do exactly the same. Now as you can see, the current here is going the other way. This is just a convention. I could have, in fact, let me change it to, actually let's leave it like this, because it really doesn't matter which way the current is going here, because whatever current we find, if we got the sign, the direction of the current wrong, then the current that we get will have a minus sign, and this will cancel in the analysis. So as you can see here, we do exactly the same. So again, we have a virtual ground, we have a virtual short circuit here actually between these 2 points, and that means that the voltage at this V plus input is equal to the voltage at V minus. Now the voltage at V plus is VI, so that means that the voltage at V minus is also VI. So let's again write V naught is equal to, now V naught in this case, because the current is going this way, this voltage is considered to be higher, so we have that V naught will be equal to VI, the voltage here, plus I times resistor R2. That means that because the voltage VI is smaller than V naught, then V naught has to be equal to the voltage VI plus the drop across resistor R2, which is simply equal to I times R2. So now we need to just find the current going through there, and we'll know what is V naught. So I, the current going through here. Now to find this current, the current flowing through a resistor R2 here, so this is R2, the current flowing here is exactly the same as the current flowing in here. That's because no current is flowing in here into the minus input, so all the current flows here. So we can easily find this current by using Ohm's law here. So the current is going from here to there, so that's VI here, and this is 0 volts here. So the current is simply equal to VI minus 0 divided by R1, and so I is simply equal to VI divided by R1. So that means, so this implies that V naught is equal to VI plus R2 times I, which is equal to VI over R1. And then finally V naught is equal to VI. Let's just factor out the I. So this 1 plus R2 divided by R1. This can also be rewritten as VI times R1 plus R2 divided by R1. This is V naught. So again, we have found the gain. So for the for the non-inverting configuration, the V naught is equal to VI times this term here, this factor here. So that's R1 plus R2 divided by R1. So again, the gain G is equal to V naught divided by VI. That's equal to R1 plus R2 divided by R1. So the first thing you'll notice is that for the non-inverting configuration, the gain is positive, and for the inverting configuration, the gain is negative. Okay, so I just wanted to give you an overview and look at the difference between these two and derive the analysis formulas for both of them. So thank you very much for watching.